Olga.
All right. So I'm going to talk about Wilson surfaces, and this is an object which we defined quite some time ago in 2015, but recently it got a new life and even gave rise to some new mathematical structures, which I mention later on in the talk. So I'm going to talk about Wilson surfaces in the new context of some generalizations about odd and generalized Wilson surfaces. And most of this talk is joint work with Vladimir Salnikov. And I still don't manage to, okay. Does anyone need to let me in? I'm sorry for the iPad.
Recording in progress.
Okay. Are you able to? Are you able to see it?
I see it.
Okay, great. Okay, so I'm going to talk about odd and generalized Wilson surfaces, and as I said, this is based on joint work with Vladimir Salnikov. So I will start with this slide because always I always forget in the end of the talk to turn the page to the last slides. So, and my co-author is very upset about that because traditionally he chooses a picture for the thank you notice. So I thank you for your presence and for your attention, and we are ready to go. So Wilson surfaces are mostly the observables in the arising in the context of gauge theories. And gauge theories, as I'm sure you know, I will just give a brief reminder. From the physics point of view, they are at the core of our understanding of our current understanding of the laws of physics. An example of a gauge theory is electromagnetism with the gauge group U1, abelian gauge theory, and the standard model as well, unifying electroweak and strong interactions is also a gauge theory with the gauge group U1 cross SU2 cross SU3. And the physical idea behind is that the system or an object in a physical system is undergoing symmetry transformations independent at each point of the space-time. Geometrically, this can be visualized as attaching a certain space, a space of these transformations to each point of the space-time. And since these transformations form a group, this corresponds to attaching a group to each point of the space-time. And in mathematics and geometry, the adequate theory describing this kind of geometry is the theory of principal G bundles, their connections and curvatures. So the general setup for a gauge theory from the point of view of geometry is given a compact connected Lie group G, there is its Lie algebra, then trace stands for invariant product on this algebra, and the gauge connection defined on the principal bundle, which corresponds to physics notion of gauge potential, is a one form on this bundle taking values in the Lie algebra. Then the curvature of this connection corresponds to the field strength. And it is a two form So you can see the formula on the screen. Oh. You can see the formula on the screen. It is a two-form defined on this bundle, also taking values in the Lie algebra. And then we are interested in certain quantities which are gauge invariant under the gauge transformations. Just to mention, physicists, by abuse of notation, often call the group G, the structure group of the principal bundle, the gauge group. So this just a small remark. And then we are interested in some quantities, gauge invariant quantities, which can characterize in some sense the theory. They are called observables, and they can be naturally classified by the dimension. For instance, there are local observables which correspond to the values of fields at certain points, or to the correlation functions of fields at a certain number of points. And then there are non-local observables. And an important example is a Wilson line, a Wilson loop, if it is a closed line, which characterizes the transport of a charged object, charged with respect to the gauge field. In electromagnetism, this is electric charge. It defines parallel transport of such an object in the gauge field. And usually the Wilson line represents a certain phase, which such a Wilson loop represents a certain phase, which a charged object, a charged particle, gains while being transported along a loop and returning to the same point. So in this space it returns, its state is the same, but from the point of view of the gauge field, it is changed by this phase factor defined by the Wilson loop. And the Wilson line is described by the holonomy of the gauge field. So here, so this path-ordered exponential stands for holonomy. And it is defined also by the closed curve embedded in the space-time, and also by the finite dimensional representation of the group G. So this is the, you can see the formula on the screen. It is well known. Then the gauge field A, the connection, it takes value, as I mentioned, in the Lie algebra of the group. And the object is made gauge invariant by taking the trace in some representation of the group, finite dimensional irreducible representation. As you can see, this formula, so it has geometric origin, but it is not easy to work with. So it arises as a solution for the parallel transport equation, and this path ordering, it usually complicates all the computations in the case when G is non-abelian. So there was some work done by Alexey Fadeev and Chetashvili, where this formula was rewritten in a different way. So if you can notice here, if you look at this formula, you might notice striking resemblance to the partition function formula for some quantum one-dimensional theory. If we replace the connection with the Hamiltonian, if we replace the representation by Hilbert space, so we will get the partition function, and here the path-ordered exponential will stand for the time evolution operator. This was noticed, and then it was actually described that such a partition function corresponds to the quantization of coadjoint orbits. And then Alexeyev, Fadeev, and Chitashvili, they suggested a different way to quantize coadjoint orbits. To remind you, the coadjoint orbit is the orbit of the action of the group on the dual of its Lie algebra. And since in our case we were working with matrix Lie groups, we can write down such an action as matrix conjugation. So here we have G, an element of the group. We have lambda, a representative of the dual algebra. And the orbit is defined by the object by such lambda conjugated by all the elements of the group. And then, so to put in correspondence the quantization of coadjoint orbits and Wilson lines, it was necessary to put into correspondence the Hilbert space of a quantum system and the representation, and it was done. And actually, the finite dimensional representations, they are they provide for a Hilbert space, and at the same time, it was, as it was noticed by Kirillov, they are in one-to-one correspondence with integral coadjoint orbits. So we can actually put the representations in correspondence with the orbits, choosing an integral orbit representative, and it will correspond to the highest weight of finite dimensional irreducible representations. And irreducible finite dimensional representations are uniquely determined by its highest weights. Which live in the dual to the Cartan subalgebra of the Lie algebra. And this is how all the pieces come together. And then the Wilson line observable, another presentation for the Wilson line partition function was given through path integral quantization of a symplectic phase space, and coadjoint orbits are symplectic spaces. This is also was shown by Kirillov. And then, and I guess not just by him, also Kirillov and Kostant and Suryo were defining the symplectic form on the coadjoint orbits. Nevertheless, the presentation, path integral presentation for the Wilson line works in the following way. So we define some certain fields. There is a field G, which takes value on the, which is a map from the curve gamma, where the Wilson line is defined to the group G. Then there is our connection, which is a one form. And then there is the highest weight of the representation, which is at the same time the orbit representative. And then there is an auxiliary field B defined on the curve and defined on this loop, which takes values in the dual of the algebra. But more precisely, it has the following properties. It has the following properties: that it takes that representative lambda and conjugates it by the group element. So actually, the field B takes values not in the entire G star, but it is constrained to take values in the orbit. And then there was this path integral defined, which corresponds to the partition function for the Wilson line. And then the action for this path integral is given by the following formula. So this is an integral over the loop. And here we have the trace of the field B, and here we have this expression, which in general corresponds to the path integrals quantization of symplectic phase space with the action something like so this is some space. Here we have alpha minus Hamiltonian, and here alpha is symplectic potential such that taking the differential of it, at least locally, it is a one form which, taking differential of which we get the symplectic form. Okay, so this is how the action for the Wilson line is defined. And then this is where we started in 2015, and we said, okay, maybe we can generalize the Wilson line to a Wilson surface, and the name Wilson here stands just for historical reasons. In analog with Wilson line, actually Wilson, who introduced the Wilson line, has nothing to do with that. So we thought of a two-dimensional observable defined, a quantity, gauge invariant quantity defined on a two-dimensional surface, a two-dimensional manifold or a sub-manifold within certain gauge theory. And we thought, okay, what if we just, by Stokes' theorem, take an open surface for the moment, and then we get an integral corresponding to the bulk, to a surface enclosed into the Wilson line. So we did that. We get some quantity, so we get something corresponding to the bulk with the Wilson line on the boundary. However, this for the moment cannot be a general formula for the Wilson surface because it is dependent on the information on the boundary. However, it was noticed that so we wrote down a definition for that, that this is actually an equivariant form on the quadrant orbit, and it can be defined independently on any kind of a surface, even on a closed surface. And we can actually work with this formula with respect to any two-dimensional orientable surface. And then it was also noticed that this formula defines an equivariant extension of Kirillov-Constant-Suryo symplectic form on the quadrant orbit. I will skip this equivariant cohomology definition. The next step was to actually notice that this is this formula actually corresponds to the Poisson sigma model on the with the target, the quadrant orbit. So a short reminder: a Poisson sigma model is defined with a Poisson manifold as a target, and then some two-dimensional manifold as a source, and it is given by a map from a two-dimensional manifold to the target manifold. And here we have the fields, one forms representing the gauge fields of the Poisson sigma model, and then the map from the source to the target. And here the action function is given by the following formula, and it includes Poisson structure. In case when this Poisson structure is invertible, the Poisson manifold can be considered symplectic as well. And then on the quadrant orbit, which is symplectic, and it is Poisson at the same time, since there is a Poisson structure, linear Poisson structure given by the structure constants of the dual to the Lie algebra. And actually the symplectic form here Kirillov-Kostantsuriov form is given like this, which can be defined through the lambda, through the orbit representative, or it can be defined through the field via the field B, which is the conjugation by group elements of this element lambda. Then an auxiliary field can be introduced, one form on sigma, on the two-dimensional manifold, taking values in the Lie algebra. And then we can define the Poisson sigma model on the quadrant orbit in the following way. So the Poisson structure here is given by B, and then there are structure constants hidden here in the alpha squared, which is actually a commutator of two forms taking values in the Lie algebra. So this is a small remark how this computation is done. The important fact here is that this action is not equivalent to this action, which is the integral of the symplectic form, but it is equivalent to it. If we integrate, if we put it inside the path integral, so we have the integral here over d alpha dg. Here we include the action. So if we integrate over alpha, we will get the integral including this the action with the quadrant orbit. So these are two equivalent actions. Now, what happens with the action for the Wilson surface? In the beginning, we had. Let me go back for a moment. So we had this action. So here FA stands for the curvature, and dA stands for the covariant derivative of including the connection A. We do here the same trick. We include an auxiliary field here. We subtract. But now here, instead of the differential, there is this covariant derivative. And instead of this formula where we have connection alpha, we get, after certain transformations and computations, we get something else. We get actually the curvature of the new connection, which is A plus alpha. So this is a connection modified by the one form alpha. And now F is the field strength or the curvature of this new connection on the same principal bundle. Here, this gives us BF theory as well. And BF theory, Poisson sigma model with linear Poisson structure produces BF theory. This is what is expected. But now we have a modified connection. So this is the action for another form of the action for the Wilson surface observable. And all these transformations, they are not just for elegancy, they're for elegancy as well. So we can see it as Poisson sigma model, which will be useful for generalizations, as we will see later on. And actually rewriting it as a BF theory actually gives a way to quantize the Wilson surface observable or a Wilson surface theory, because now, since we have an action corresponding to BF theory, we can also say that we have a topological two-dimensional theory, where now, like the we just need to remember that the field B is now constrained to take values in the coadjoint orbit, since it is a conjugation of the orbit element. In a usual BF theory, the field B takes values. So it can be defined for any dimension, and sigma is the manifold where it is defined. In this case, it is two-dimensional. In the usual case, it takes values in the entire dual Lie algebra. And as we know, coadjoint orbits foliate the dual of the Lie algebra. So they are symplectic leaves inside inside the dual, inside G star.
So, Olga, I'm sorry. So your Poisson sigma model is actually symplectic, or it's Poisson? Where does it take values?
It takes values in coadjoint orbits. So it is
so it's symplectic.
sigma model. It is symplectic. Yes,
it's
yes.
a symplectic. Okay, thank you.
Can I also ask at this point to clarify something?
Yeah. Sure.
So you're talking about quantization of this Wilson surface as an observable. Can you just clarify what you mean? Just as a bit of context, are you talking about
I haven't
about this in
about this. I just mentioned that this BF form will be useful for that.
Okay. Will you explain what you mean by quantization?
Yes. I'm
okay.
Okay. Yeah.
Okay. All right. Thank you.
Not the geometric quantization, just canonical quantization. Okay. So then it is known, it was done by Migdal, and then it was done by Witten as well. Maybe by some other people too. So there is a canonical quantization of two-dimensional BF theory. So we write the partition function. So, and here the partition function is defined for each class of principal G bundles over the surface. So this is two-dimensional BF theory. And for each class, there is a sum over the representations. And here, so this stands for the character of the representation. And then Ci stands as an element of the subgroup of the center of the covering group for the gauge group. So the gauge bundles, the principal G bundles are classified by the elements of the fundamental group of the group G of the structure group. And these correspond to the subgroup of the center of the covering group in a way that we define G by quotient of the covering group by the subgroup of, by the normal subgroup of the center. And the CIs are standing for the central element. So there is this, and by quantization, I mean just this, that we can define the partition function of a quantum system.
Sorry, so can I clarify at this point? So you're now taking this two-dimensional field theory on the Wilson surface, and
Not yet. So this is just BF theory. This is just a reminder how two-dimensional BF theory, the quantization for two-dimensional BF theory. But now, since the Wilson surface is defined as a BF theory with certain constraints.
Yeah, but still, I just want to clarify the terminology. What exactly you mean by quantization? Because you started talking about, higher dimensional gauge theories, and they can be quantized, of course. But then you were talking about these observables that live on lower dimensional manifolds, and they themselves have certain actions associated to them. So what are you quantizing exactly?
I am quantizing this two-dimensional object.
Okay, and by quantizing you mean compute the partition function?
Partition function, yes.
Okay, you're not doing any Hilbert spaces, any self-adjoint operator is nothing like that.
No, I'm not doing that, but there is actually Hilbert space which corresponds to the representation of the
Okay, but it just appears in the action
yes.
of the theory that you're integrating. Okay, all right, thank you.
All right, so this is for how the partition function for each class of principal bundle looks like. So for each central element in the subgroup of the center of the covering group. And then we sum, to obtain the entire partition function, we sum over all the classes of principal bundles. So this is just the BF theory, a regular BF theory with the field B taking values in the G star in the dual of the Lie algebra. And then we say, since our theory is a BF theory in some sense as well, we can quantize it in exactly the same way. But what happens now, since the B field takes values only on the orbit, it means that we choose only one particular representation. So here the sum over the representations disappears, and as a formula for the Wilson surface, we obtain just the which will turn out to be a phase factor. So for each class of the principal bundle, for each central element of the covering group, we obtain the character of this, the character of the representation computed on this central element, and then dimension of the representation stands for the normalization factor. So this is the formula for each class of the bundle which we obtain. And then we can actually couple this Wilson surface to some background two-dimensional gauge theory. So here, if we, for instance, we can take the same BF theory in the background, and we can couple it to the Wilson surface. It will multiply the partition function for each class of the bundle, and then the total sum, the interacting partition function, will be summed over all the classes of principal bundles. And we call this topological interaction since both theories are defined on the same principal bundles. Both connections are defined on the same principal bundle. Now, so this is where actually the new story begins. We decided to go through certain generalizations. So we thought that we can go into the direction of supersymmetrizing this to add some odd degrees of freedom to the entire model, to add odd degrees of freedom to the structure group, we could add odd degrees of freedom to the target, we could add odd degrees of freedom to the source. And we started with adding odd degrees of freedom to the target. But what does it mean? The target is a coadjoint orbit. So this is the orbit of the action of the gauge group. So we add odd degrees of freedom to the structure group. And which is helpful now is to study linear Poisson sigma model. It's supersymmetric version with supercoadjoint orbit as a target. So this is what we started doing and looking at certain examples. Now, the super Wilson surface action functional will be looking exactly in the same way as it was before, but now the fields are superfields. So the matrix Lie supergroup G is now characterized by the even Lie group, and then it has Lie algebra, which is now given by which is now super algebra, given by G0, which is the Lie algebra of the Lie group G0 of the even group, and some odd subalgebra added to that. So the fields are now superfields. The gauge potential takes values in the Lie superalgebra. The field B takes values in the can you still see the screen? Okay. Yeah, in the dual to the Lie superalgebra. And it is again defined by the conjugation, where now the element G alpha is in the supergroup G. G corresponds to the element in the even group, and alpha corresponds to the element in the odd part of the algebra. And here P, so we just take the odd part of the subalgebra of the algebra G1 to be G0 even algebra shifted by with shifted parity. And then the orbit representative is now defined as an element in the dual to the Cartan subalgebra, and then direct sum with its shifted with the odd part shifted even parts. So H1 star is the H0 with shifted parity, and then the star is taken. And then the parity shifted H0 star is the odd extension of the Cartan subalgebra. And again, there is a auxiliary field, which was defined to define Poisson sigma model, taking values in the super Lie algebra now, one form. And then there is an invariant bilinear product on the Lie superalgebra. So everything is redefined with respect to the super Lie algebras and super Lie groups. So one example goes with the Lie group U OSP 1, 2. So its algebra has 3 even bosonic generators, which are the same, which actually form the subgroup SU2. And then there are odd fermionic generators, and they form the odd subspace. So P0 with shifted parity, and where P0 actually corresponds to the invariant complement of the Cartan subalgebra in the decomposition of SU2. So we have here G0, which is SU2, which is equal to the Cartan subalgebra plus direct sum with invariant complement. H0 is U1 subalgebra, and then there is this P0. And the algebra UOSP 1, 2. So it corresponds to SU2, and then direct sum with the P0 with shifted parity. So here are some commutation relations for this super Lie algebra. And then for this subalgebra, this is not always the case for the superversion of Lie algebras. For usual even Lie algebras, semi-simple Lie algebras, we can identify G and G star, the algebra with its dual algebra, and in this way we can identify adjoint and coadjoint orbits. In superversion, this is not always the case, since since when we do this identification, when we have this super Lie algebra, when we do this identification of the Lie algebra with its dual, it is not always identification, but it can the invariant product which is used here can interchange the signs here and the parities here. So we cannot always do the straightforward identification, but we took this example of UOSP because in this case the identification works. And we computed some examples considering the orbit representatives. So first we take purely even orbit representative. We take an element where we have the element of the algebra in the so this is an element of the superalgebra. Instead of the dual. Now we are looking at adjoint orbits in this case. So for the even element, we have only the even part here. The odd element is equal to 0. And then we compute the stabilizer, which stabilizes this element. And this is also turns out to be purely even. This is just U1 subgroup of this of the supergroup UOSP12. And then the orbit is computed by taking the quotient of the supergroup by this stabilizer of this element, the orbit of this element, and we get the sphere multiplied by R2 with shifted parity. Just to recall, the stabilizer of SU2, the orbits of SU2 are just spheres. So here we get some odd part to the coadjoint orbit manifold. So this actually this is enough. Because as I mentioned, we are looking at the elements here which take values in the direct sum of the dual to the Cartan subalgebra and its odd counterpart. And we see that in UOSP algebra, there is no odd counterpart for the Cartan subalgebra. So as we when we were looking at the structure of the algebra, we see that we only add the invariant complement to the Cartan with the shifted parity. This is the odd part of the Lie algebra. And then we compute partition function. Now we take the character, which is the character of the representation computed on the central element, and this representation corresponds to the orbit element x beta, and this is now super trace, and as D stands for, so to say, super dimension of the of this matrix, where the number of non-trivial diagonal elements of the even block minus the number of the diagonal elements of the odd block. Okay. So structurally, it looks the same. Again, we define such a formula for each class of the principal bundle. And then we identify highest weights of the representations. And in the case when the target space of the theory corresponds to the quadjoint orbit with the representative x0, the orbit passes through this point x0 in the dual to the Lie superalgebra. And in this case, actually, there is only one trivial class of principal G bundles over a closed surface. The even part of the group is SU2, which is simply connected. This means that there is only one trivial bundle over a closed surface. And then the partition function is computed only for the identity element as a central element. And it is equal to 1. Actually, this corresponds to the non-supersymmetric case of SU2. The partition function is exactly the same. So we introduce the what we call, so to say, Bosonization conjecture, which states that if we have only even part, if the Cartan subalgebra does not have an odd counterpart, the partition function will not, the partition function of this modified super Wilson surface, where the target is now superspace, superquadjoint orbit, the partition function will not be different from a regular Wilson surface. But we expect different values for the partition function in case when there is an odd counterpart to the Cartan subalgebra. Okay. So to illustrate that, just without doing these computations, we introduced such an example, which we first called twisted SU2. Now it got modified to weird super Lie algebras. Weird Lie superalgebras. So actually, what we wanted to do is to get that element corresponding to the orbit representative to make it odd, and which actually this element enters into the into that phase factor, into this exponent of the Wilson surface. We just wanted to make it odd. And to simplify things, we just thought, okay, we take the case of SU2. We look at the orbits of SU2, which are two-dimensional spheres foliating R3. And we say that the radial direction, we change parity of the radial direction. So the spheres are still even, but now the radial direction is odd, and the parameters labeling these spheres, the parameters labeling the orbits, are now odd. So this is our G star, which is isomorphic to R3, and the orbits are isomorphic to two-dimensional spheres. If we want to look at an algebra corresponding to that, this would be So let's say we take our SU2 algebra, we decompose it into U1 and into its invariant complement. And now what we do, we shift the parity of the invariant complement. So we get something which we called later weird SU2. And I will explain in a moment why we called it weird. So, and we get something, we get some superstructure, we get grading, we get even part, which is, no, sorry, that's the other way around. So we shift the parity not of the complement, but of the subalgebra. So now the subalgebra U1 is odd and the invariant complement is even. But then we say this is not a Lie superalgebra according to its standard definition, because what happens here, first of all, there is no even subalgebra, which might correspond to the even Lie group here. And second, if we look at the commutators, the Lie bracket is now not, the bracket is not a Lie bracket now, the bracket becomes odd. And we wanted to look at such structure a little bit more in detail. And first we thought that there is nothing else to that, but except some three-dimensional cases, because otherwise the commutators will not close and nothing will work. But it turns out that this is not the case. So actually we got some kind of a spin-off, which we call now weirdly algebras. It's now work in progress with Alexei Kotov and Vladimir Salnikov. And we can actually study such algebras if we have a regular Lie algebra, in even one for the moment, which with its symmetric decomposition. So let's say we have H. It decomposes into direct sum. Here H is a subalgebra. And we thought that there is nothing more of this type, just three-dimensional Lie algebras, because we, in the beginning, we only were considering Cartan subalgebras, but this is not the case. Actually, it has to be, when we go to high dimensions, this has to be something else. And then this is a subalgebra. And this is H module. It is an invariant complement. It is not a subalgebra. And then there should be the commutators working in this way. So if we have commutator of H and H, it closes in H, since this is a subalgebra. The commutator of M and M closes in H, and the commutator of H and M is in M. So this is odd, even, odd, even. Okay. And then starting from this structure, we can shift the parity of the subalgebra. So we get something which we called weird. And we shift the parity of the bracket. And we get some kind of the algebra which works in this way. The commutators still work. So there is some additional structure needed. We are still working on that, but this looks like an interesting example, especially taking into consideration that if we, after we change the parity of everything here, if we take this weird example and shift the parity of all the subalgebras and shift the parity of the bracket, we obtain a super algebra. So so now H is even. So this is super algebra H with the odd part, the module, the invariant complement with shifted parity. And for here, actually, there is a, if we integrate it, there is a super Lie group corresponding to that. So there will be a group with the even part H, and then the algebra, if we write Harishchandra pair, H direct sum with M. And in this case, it is interesting to study where this thing integrates, actually, because there is no even group corresponding to that. The even part, if we integrate that, does not give the group structure. So we are going to study what is going to happen there. So on the level of the algebras, since shifting of parity, by shifting parity, we can go from weird to super, there is probably no new information. But on the level of the group structure, when we integrate these objects, something interesting should come up. So this is a spin-off about some mathematical structure which came up while we were working on the project. And then I wanted to mention some generalizations. I will not go. I will not talk about this in a lot of detail. Just that we can actually work on theories gluing or on observables by gluing such Wilson surfaces through one-dimensional boundary, and we can map such constructions as one into one target space, into one coadjoint orbit, or into different ones. And also we can consider, so this is what is given here, we can consider such observables with different gauge groups above them, the different structure groups. And then there is a construction which might be useful for that. It was introduced by Pavel Shevera, if I'm not mistaken, which is called quilted surfaces. So they were studying moduli spaces, and I would probably look at some action functionals corresponding to, and some geometry corresponding to that. All right, and so this is basically all I wanted to say. The talk is based on several papers. Some of them, as I mentioned, were quite old, and so here there is some new life starting. So there were papers, quantum Wilson surfaces, topological interactions, Wilson surface observables from equivariant cohomology, and then the recent paper, which is called odd Wilson surfaces, where actually the odd Wilson surface, we said that it that actually weirdly algebra gives rise to an odd Wilson surface. And now since I started with that, I will not forget about the last slide, and I will thank you again for your attention.
Thank you. Thank you, Olga. Any questions? Okay, let me ask. So I think you mentioned somewhere the super holonomy, right? Or did I hear it?
No, I didn't mention super holonomy, actually.
Okay, but okay, that's probably in my head. But so, but is it involved in the construction for super? I mean, in the super generalization of Wilson
No. What we did actually, we said that we can profit from Poisson, from this presentation of the Wilson surface as a Poisson sigma model, and we can go directly to super Poisson sigma model. We can, of course, go the other way around, just we did with the regular Wilson surface. We started from the Wilson line and we generalized it to the Wilson surface. We can define the super Wilson line and then go to super Wilson surface. Probably it will be more complicated because yes, there is.
Is it possible? Is it possible to do?
It should be possible, but it will be very technical because in super case, non-abelian Stokes theorem, probably it will require some definitions. I think it is working, at least for some cases, but it will be very technical to define properly, redefine all the objects for the super case. And all the operations.
Thank you. More questions?
Yeah, if I can ask. By the way, thank you for the nice talk. I just wanted to clarify what was the role of these path integrals with respect to the original definition of the Wilson line observable. So the Wilson line observable was defined as an integral over this curve with respect to a connection where the connection is a dynamical field in some gauge theory, and then this formula defines an observable for that gauge theory. So you started talking about some action introduced on the line where the Wilson loop was defined, and then you generalize that to surfaces. So what was the relation of that action that was introduced to the original Wilson loop integral?
That's the different presentation of the same thing. So this path integral, Feynman introduced it to describe the partition function. So, so here we say that there is a partition function, and we can rewrite it as a path integral.
Okay, so the what identities do you need to do to evaluate the path integral and show that it's equal to this integral over the Wilson loop?
So you need to put into correspondence the Hilbert space and the representation. And I think this is Weil-Bott theorem, which says that irreducible finite dimensional representations correspond to the irreducible finite dimensional representation corresponds to the Hilbert space. So if you look at the quantization of the symplectic phase space of the coadjoint orbit, more precisely, so I think probably no, I think you do not need geometric quantization for that, but you. Okay, so what is the procedure? You state that there is a correspondence between, there is a certain relation between the curvature form and the symplectic form, and the theorem that states that your Hilbert space corresponding to the holomorphic sections of the line bundle over this over the coadjoint orbit will be isomorphic to the representation. So you put into correspondence Hilbert space and the representation, and then you say that your Hamiltonian here, which is A, which is a function on the orbit, no, the other way around. You can rewrite your connection as a function on the phase space, and
so if this is outside, the scope of your talk, it's okay. But I wanted to just to understand what was the analog of this identity for your two-dimensional Wilson surfaces. So if I understood correctly, on the right-hand side, you had this path integral with respect to a different action on the Wilson surface. But what is the left-hand side? Is that this sum over characters over some central elements, or in
the left side, or on the
yeah.
right? On the left.
Well, on the right, I understand you have this path integral formula. So what would be the analog of the left-hand side, where you have this geometric integral, so this exponential trace of this line integral?
So there is this on the level of the surface, you mean? So there is this thing. So here you have a partition function, but the sum over the representations is has disappeared because we have chosen only one representation.
Okay, so I just wanted to understand, how does this formula depend on the original gauge field A? Because in the one-dimensional Wilson line, it was obvious from that equation on the previous slide. So here, to me at least, it's not quite clear how the result of evaluating this path integral now depends on the original connection A.
Oh, these are the holonomy elements. So here
So each of these chi C's is itself a holonomy. So it's like it's a Wilson line in itself. Okay, so then it's a combination of those formulas that you had in the previous slide.
So, but just for the BF theory, which is in the background, this is just connection A. But here, the holonomy will be of the new connection, which I mentioned when we introduced this auxiliary alpha field. So here, there will be holonomy of the connection of A plus auxiliary field, which appeared here.
So each one of these chi C's could be written as a regular Wilson loop.
Yes.
Expression. Okay. Okay, so that's what I wanted to clarify. All right, thank you.
So in here, as you put in correspondence what I wanted to say here. I was looking for words. So the function, so the Hamiltonian function with relation to the basis elements here in G in algebra G. So here the A taking value, so we can consider it as a background field, and taking value in the Lie algebra. So there are here some generators sitting here. So we can construct Hamiltonian out of this Hamiltonian function coupled to the generators of the algebra. So this is how we put. So probably this is not what you meant, but if we look at the partition function, so there is this trait for the Hilbert space, and then there is path-ordered exponential of the Hamiltonian. So here, normally this is not a closed time contour, but we can put periodic boundary condition and put this into the correspondence. And Weilbot theorem puts in correspondence here the Hilbert space as a space of the holomorphic section of the line bundle over the orbit with the representation of the group G, finite dimensional reducible representation.
Okay, thank you.
Thank you. Thank you, Igor. Thank you, Olga. More questions? Okay, if no, then let me thank the speaker again.